So 4.5 is all about rational functions, and there is a lot to do with rational functions. And I've mentioned it before, but I'm going to mention it again. If you are in a math class and you hear the word rational, you need to think fraction. So rational functions look like p of x over q of x, where p of x and q of x are polynomials, and obviously we don't want our denominator to be 0. That's a big thing. There is a special note there that says the domain is negative infinity to positive infinity, except for the values that make q of x equal to 0. Those are the trouble spots. We've talked about those in the past, and they come up here. If you have just a solid whole number in the bottom, then you're not going to have any trouble spots. If you have an x or anything like that in the bottom, then you will have trouble spots that you have to eliminate out of your domain. And so that's what we're going to do first. We're going to find the domain of these different rational functions. And the thing to remember is your starting point is that negative infinity to positive infinity, and then you just want to remove anything that makes the denominator 0. So if we look at this first one, we have 1 over x. What value or values make the denominator 0? Yeah, when x is 0. That's our trouble spot. So we need to write the domain in such a way that we do not include that. So if we're doing step builder notation, step builders where you have the curly bracket and the curly bracket and you have the x such that, you would have x such that x does not equal 0. There's your domain. I would say that's probably not the way you're going to be asked for it most of the times. If you're asked for your domain, you're going to be asked for it in interval notation. An interval notation is where you're going to start with your lower limit, which is negative infinity. You're going to go up to 0, and then we use a parenthesis because we don't want to include 0. Then we use that special union, parentheses 0 to positive infinity. So we list out negative infinity to positive infinity, but we take out any single spots that's going to cause trouble. And here's the nice thing, is if you write it out in interval notation, you will always have a union wherever that trouble spot falls. So on either side of your union should be your trouble spot every single time. And that's regardless if you have 1 trouble spot, 2, 3, 8, however many you have. So let's look at B. We have g of x equals x minus 3 all over x squared plus x minus 2. So we need to figure out where our trouble spots are. Our trouble spots are going to come when our denominator equals 0. So we need to factor it. It's a quadratic, yeah? So we're going to factor where we have x and x. The sign in front of my c is negative, so I'm going to have a positive and a negative. I need factors of 2 that subtract together to give me a positive 1. So I need to have more positives than negatives, so I'm going to have a positive 2 here and a negative 1 there. Set each of those factors equal to 0 so that I find that x is negative 2 and x is positive 1. If x is negative 2 or if x is positive 1, we're going to get zeros in our denominator and it causes a problem. So this time we have 2 points we need to eliminate. If you wrote it as step builder, you'd have x such that x doesn't equal negative 2 or positive 1. Again, you probably won't see it that way, but just in case. The way you're probably going to see it is with your interval. So you still start with your lower limit, and you go negative infinity up until you hit your first trouble spot. The first trouble spot we're going to hit is going to be negative 2, because negative 2 is less than 1. So we'll hit negative 2, we'll union, we'll go negative 2, and then we keep moving on our interval until we hit our next trouble spot, which will be positive 1, union, and then 1 till positive infinity. So when you have 1 trouble spot, like in our first example, we have 1 union. We had 2 trouble spots, so we have 2 unions. Because remember, the unions are going to show up exactly where our trouble spots are. Questions? Okay, what's our trouble spot for our last example? Yeah, because we'd said x plus 1 equal to 0, so x is negative 1. So how would I write that as an interval?
Negative infinity to negative 1 parentheses union negative 1 to positive infinity.
Perfect. That's exactly right. Questions on how we find the domain of these rational functions? Okay. The next bit that we're going to talk about is something called vertical asymptotes. You ever heard about asymptotes when it comes to graphing? The line x equals a is a vertical asymptote of the graph f if f of x increases or decreases without bound as x approaches a. And you're like, okay, that's a lot of stuff. What it means is an asymptote is this imaginary line of sorts that your graph is going to get really, 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 really close to. Okay? When we talk about vertical asymptotes, your graphs will never cross those. So they hug. So you want to hug your asymptotes. You don't want to cross them. And so these are the 4 different ways they can look, because you can be headed to positive infinity in terms of your y's as you hug your asymptote, or you could be headed to negative infinity as you hug your asymptotes. And you could be approaching from the left-hand side of your graph, or you could be approaching from the right-hand side of your graph. So these are the 4 different ways they can look. Again, you will never actually cross your vertical asymptotes. The important thing is finding the vertical asymptotes. And that's what the bottom notes tell us. Vertical asymptotes happen where q of x equals 0. So that's our denominator. So the nice thing is if we have to find our domain, we're already playing around with this and we're already finding these trouble spots, which actually end up being our vertical asymptotes. Now, there is a clarification between vertical asymptotes, though, and holes in our graph. Vertical asymptotes happen where q of x equals 0 when our rational function is already simplified. Holes happen where q of x equals 0, but it hasn't actually been reduced yet. And so we're going to see some examples that's going to make a lot of sense in just a second. But regardless, vertical asymptotes and holes both are your trouble spots. It's just the holes will simplify out and reduce out. You won't see them in the final end, but there's still a hole there. And again, we'll see that in a minute, where the vertical asymptotes are at the final stage. Okay? So trouble spots, it's where your denominator equals 0. So let's look at it. We're going to do 3 of them so that we can find some vertical asymptotes and some holes. The way we find our vertical asymptotes or our holes is we look at our denominator, and we're going to have to figure out those trouble spots. So for this first one, I have 2x minus 11 all over x squared plus 2x minus 8. So I have a quadratic in the bottom, so I'm going to try and factor it. They're going to have opposite signs, so I need factors of 8 that subtract together to give me a positive 4. Or, excuse me, positive 2. I'm going to need a positive 4 to subtract against my negative 2 to give me that positive 2 in the center. Now, notice when we get to this step where the bottom is factored, we always want to ask, is there anything that the top has in common with the bottom? Can I reduce anything? And the answer is no, because 2x minus 11, I can't simplify that any further to get either x plus 4 or x minus 2. So this is fully reduced. So we are good here. So now if I'm finding my vertical asymptotes, I'm going to look for my trouble spots. My trouble spots happen at x equals negative 4 and x equals positive 2. That's where my vertical asymptotes happen. I shorten that to VA. So that I have a vertical asymptotes at x equals negative 4 and x equals positive 2. Because I can't have my function have those values, because if they have those values, I get a 0 in the denominator and it doesn't work. So thus we have asymptotes there. That's where our graph will hug those two respective lines. Vertical asymptotes will always be x equals a number. Always. Because they have to be vertical. And we get vertical lines by x equals. Questions on that one? All right, let's look at the next one. We have g of x equals x squared minus 4x all over x to the third minus x. So notice that on top, I could factor out an x, leaving me with an x minus 4. And on bottom, I could do the same thing and get an x squared minus 1. That means it's not reduced yet. But here's a question. If I reduce it, which we're going to reduce it, that means I'm going to mark out right here. I'm going to mark out those x's. Tell me what happens, though, when I mark out those x's. If I plugged in 0 in the original problem, would that cause a problem? Like, is 0 going to be a problem spot?
Yes.
Yeah, because I'd have 0 minus 0 in the bottom. But I just marked it out. So you would think that's not going to be a trouble spot, but it is. This is how we get holes. Holes are trouble spots that get eliminated. And so as we progress on, here we're going to have x minus 4, and then this is the difference of squares, so we have x plus 1, x minus 1. Notice that 0 is not going to come up as an asymptote, but 0 has a hole, and it's because we canceled it out early on, and that's how you get those holes. So if during the elimination and the simplifying process something cancels that would still originally have caused a problem, that's a hole. So we have a hole at x equals 0. Then a hole in a graph is exactly what it sounds like. You have your graph, and then there's literally a hole right there at that point where the graph would be discontinuous. So we have a hole at x equals 0, and then over here, we have vertical asymptotes at -1 and +1. So you can have both in the same graph. You can have holes and you can have vertical asymptotes. They're going to look different as you graph them because a hole is just where you jump that one point. A vertical asymptote is a line that your graph is going to hug. So if you are working through a problem and stuff starts eliminating out, you need to make sure that you're not eliminating zeros that you forget about at the end. If you're eliminating numbers, like a 2 and a 4 or something like that, those have no effect on any of it. But if you eliminate out some x's, or even later on, do I have that coming up? No. Like if this had been a 1 on top instead, and this had been x minus 1 over x plus 1 over x minus 1, then those would have canceled, leaving me with just x minus 1 as a problem. But this one would have been a hole, because it eliminated out and still would have caused an issue at the beginning. Does that make sense? Okay. Let's look at our last example. We have x minus 2 on top. And then on the bottom, we have x to the third minus 5x. So I can factor out that x, leaving me with x squared minus 5. Well, nothing cancels, so that's good. So I'm going to have x equals 0. That's a trouble spot. And then x squared minus 5 equals 0 is where I'm going to get my others. I'm going to add the 5, square root both sides, so that I get x equals positive radical 5 and negative radical 5. So I have vertical asymptotes in 3 spots. At x equals 0, x equals positive radical 5, and x equals negative radical 5. You can have radicals as your asymptotes. On a test, I would never ever try and make you graph asymptotes that have radicals, because that's mean. But you can algebraically get them. Questions? Okay. If you can have vertical asymptotes, you can have horizontal asymptotes. Horizontal asymptotes, again, are a line where your graph is going to hug it. There is a slight difference here in that a horizontal asymptote can be crossed. But if you cross a horizontal asymptote, you're still going to hug it. So you could have a graph with an asymptote like this, and your graph comes up and then comes back down and starts hugging. You don't see that very often, but it can happen. You can cross horizontal ones. You cannot cross verticals. On a test situation, I would never give you one that crossed because I think that's annoying. But there's nothing algebraically wrong with them crossing. These will always look like y equals because we get horizontal lines from y equals some number. And finding horizontal asymptotes is a little bit more work than finding our vertical asymptotes. In order to find horizontal asymptotes, you have to look at the degree of the denominator and you have to look at the degree of the numerator. Numerator and the denominator. I said those backwards. If the degree of your numerator is less than the degree of your denominator, so if the top is less than the bottom, then you have a horizontal asymptote at y equals 0, always. If your two degrees are equal, so like you have an x squared over an x squared situation, then you're going to look at your leading coefficients of those numbers. We're going to do examples of all of these, I promise. And so y will be the ratio of those two leading coefficients. If the top is greater than the bottom, then there are no horizontal asymptotes at all. So those are the three cases. If the top is greater, if the bottom is greater, or if they are equal. And then the last thing, because I couldn't figure out how to lay out the notes well when I typed them up, was I went ahead and stuck oblique or slant asymptotes here at the bottom. Those are the fabulous asymptotes that are either neither horizontal nor vertical. If you think about driving through Joplin, think about Murphy Street. Murphy Street does not go north and southeast. I mean, it goes everywhere. It just runs straight through the middle of Joplin. It does what it wants to do. It doesn't follow the number streets. It doesn't follow the name streets. It kind of does its own thing. This occurs when the degree of the top is 1 degree greater than the degree of the bottom. So if the top differs from the bottom by 1 degree, then you're going to have an oblique or slant asymptote. I'll be real honest. These are gross. Gross. You will have 1 on your homework. I'm not even going to guarantee that I'm mean enough to put 1 on the quiz. I know for a fact I would never give 1 to you on the test. So we will expose you to them, and we will move on from that. Okay? Exposure here. Horizontal and vertical asymptotes are the bigger concern. So let's do these so we can see how it all starts to play out. The first 3 examples, we're just going to find horizontal asymptotes. And notice that the equations for our functions are very similar. Very similar. The bottoms of each of these are exactly the same. The only thing that changes is we have 4x or 4x squared or 4x to the third. There was 3 different ways we could find horizontal asymptotes, so I have 3 examples. So what we need to do is we need to look at the degree of the top, that's our n, and compare it to the degree of the bottom, that's our m. So what is the degree of the top polynomial for this first example? 1. And what is the degree of the bottom? 2. So we have a situation where n is less than m. And if n is less than m, then we have a horizontal asymptote at y equals 0. No computing necessary. For our second one, the degree of the top is what?
2.
And the degree of the bottom?
2.
So we have n equals m, and so this is where we're going to look at our leading coefficients. Our leading coefficients are 4 and 2. So that would be 4 over 2, which simplifies down to 2. So I'm going to have a horizontal asymptote at y equals 2. And the last one, the degree of the top is what? 3. And the degree of the bottom is still 2. So I have n is greater than m. And if n is greater than m, there's no horizontal asymptotes. Now, even though it doesn't ask for it, I just told you that slant asymptotes occur when the degree of the top is greater than the degree of the bottom by just 1 degree. That happens here. And so this one would have a slant asymptote. And we will do a slant asymptote here in just a minute. But notice that if you have a slant asymptote, we don't have a horizontal asymptote. And that's always true. You can't have horizontal asymptotes and slant asymptotes in the same function. You can have vertical asymptotes and horizontal asymptotes, or you can have vertical asymptotes and slant asymptotes. But we can't have horizontal and slant happening at the same time. Okay? So let's look at the next example. The next one says find all asymptotes. So we need to look for horizontal, oblique, and vertical. I always recommend starting with vertical asymptotes first. I think those are easiest to come by, and so I recommend starting there. If we are starting with our vertical asymptotes, that's where we just set our denominator equal to 0. So that's over here. Vertical asymptotes will be when x minus 2 equals 0. So x equals 2 is where our vertical asymptote will happen. Next, we would look at horizontal asymptotes. That's where we look at the degree of the top versus the degree of the bottom. What is the degree of the top?
2.
Degree of the top is 2. Degree of the bottom is 1. So n is greater than m, which means what? No horizontal asymptotes. All right. Now we're going to go look at oblique or slant asymptotes, whichever one you want to call it. All right. So how do we find an oblique or slant asymptote? I know I'm going to have one because n is greater than m by just 1 degree. This is where you're going to do some old school long division. Okay? We're going to do long division based on what the problem starts with. It tells us the x minus 2 out front, because that's what we are dividing by, the 2x squared minus 3x minus 1 underneath. You're taking the numerator divided by the denominator. What do I multiply x by to get me 2x squared? 2x. 2x times x will give me 2x squared. 2x times negative 2 will give me a negative 4x. I'm going to draw my line, change my signs, add down so that I get x minus 1. What do I multiply x by to get x? 1. So I have x minus 2. I draw my line, I change my sign, and I'm left with 1 remainder. The remainder does not matter. Here's what does. What's on top is the equation for our oblique asymptote. So our oblique asymptote happens at y equals 2x plus 1. Vertical asymptotes always look like x equals a number. Horizontal asymptotes always look like y equals a number. Oblique or slant asymptotes are always a linear equation. Again, I will not make you graph these on a test because they are gross. We do have an example in the notes where I show you how they play out, but I won't ask you to do it on a test. Questions on how we find all these different asymptotes? Okay. So let's look at how we actually are going to graph these rational functions. Let me I guess you guys have it in front of you, even if it won't focus very well here. The first thing you're going to want to find is you're going to want to find your y-intercept, if you have one. Not every rational function will have a y-intercept. If you have a asymptote at that axis, you're never going to cross it, so you're never going to have a y-intercept. But if you have one, it'll be at f of 0. So you plug 0 in, you calculate it out. Then you're going to find your x-intercepts or your zeros or your solutions. Again, if you have any. You do that by looking at p of x equals 0. So you're going to set your top or your numerator equal to 0, and that's going to tell you if you have any x-intercepts. Then you find any vertical asymptotes by setting your denominator equal to 0. That's also where you find out what your domain is, because that tells you the trouble spots, and you can find all that out right there at the same step. 4, you'll find out if you have any horizontal or oblique asymptotes, and that's where I make it really obvious. So I put an extra note in there that you can't have both. You can have one of each of them, but you can't have both. That's also where you find your holes, because your holes happen up there with your vertical asymptotes. And then the last step before you actually graph is you want to plot at least one point between and beyond your x-intercepts and your vertical asymptotes. That's because we don't really know what's going on in between those. And even after these first 5 steps, sometimes you only have one point that you found. You found all these asymptotes and you found one point on your graph, and that's not going to help you graph these things. And so we have to put some test points in there to figure out what's going on in our graph. Then we graph. So that's a lot of steps to do one graph, which is why I leave lots of room in order to do this. I'm trying to figure out if I can keep all of this up there. Maybe, for a little bit. Let's look and see how this is going to play out a little bit. Step 1, we need to find out our y-intercept if we have one. So I'm going to find f of 0. I'm going to put 0 in place of all my x's so that I have 0 over 0 minus 0 minus 2. I have 0 divided by negative 2, which is 0. So I do find a y-intercept at 0, 0. Step 2, I need to find x-intercepts or zeros. That's where I set my top, my numerator, equal to 0. So x squared equals 0. So I have x equals 0. 0, 0 again. If you find your y-intercept is 0, 0, automatically you know you have an x-intercept there as well. But we don't know if that's our only one. In this case, it is our only one. But we could have had more depending on what the top had looked like. Where am I?
You're on the other page, at the second example.
I may have skipped one. Or maybe it comes up later. Or I didn't flip over the paper. Sorry, guys. I got ahead of ourselves. That's okay. We're going to work them anyways. They're just out of order. I was like, that does not match at all. Yeah. Sorry, guys. Went a little bit out of order. All right. Step 3, find vertical asymptotes. That's where we let our denominator equal 0. So that's x squared minus x minus 2 equals 0. Sorry, what is going on up there? Always try to factor. X, we're going to have positive and negative. Factors of 2 that subtract together give me a negative 1. It'd be negative 2 and a positive 1. So x equals a negative 1 and a positive 2. That's where my vertical asymptotes are going to happen. This is also where if we were asked to find the domain, we could figure out the domain from that as well. Step number 4 is finding our horizontal asymptotes. So what is the degree of the top?
2.
What is the degree of the bottom?
2.
So the degree of the top equals the degree of the bottom. What does that tell us?
Look at the coefficients.
Yeah, we got to look at those coefficients. So what is the coefficients in front of my leading terms? Yeah. So we have a horizontal asymptote at y equals 1. Notice it's not 0. Just because there's not a number written out there doesn't mean that it's 0. We have understood ones out there, so it's 1 over 1. The last one is plotting a point between and beyond all the x-intercepts and stuff. So after the first 4 steps, you want to graph what you have. And then that's going to help you narrow down what points we're going to test. Okay? This is one of those situations where even after all these steps, we only have 1 point to plot. But we've got lots of asymptotes. So we're going to graph all of that we can down here on the graph paper. And when I slide it up, you're not going to be able to see that information. So we had a point at 0, 0. I had a vertical asymptote at x equals -1. So when you graph those, you want to use dashed lines. You do want to include arrows on those. I also have a vertical asymptote at x equals a +2. And I have a horizontal asymptote at y equals 1. So that's the information that I have. Obviously, not much of a graph is going on here yet. So now I'm going to pick some test points. And here's how I determine which ones I'm going to pick. Because you can test any point you want. But I need to pick something. Here's my vertical asymptote. I need to pick an x value or 2 that lie to the left of this vertical asymptote. So I'm going to test, let's see, that's at -1. I'm going to test -2 and -3. While the instructions say to plot at least 1, I'm always going to choose to plot 2. Because that's going to, if I just plot 1 point over here, I still don't know what's going on. But if I plot 2, I know which way my graph is angling and which asymptotes and how it's hugging and all that kind of stuff. So I'm going to test at -3 and I'm going to test at -2. Then I look between my asymptotes. And yeah, I have 1 point in there, but I'm going to plot a point between the asymptote and my point, and between this point and my asymptote. So I know this asymptote lies on -1, so I guess I'm going to go with -1/2. I know you guys are like, ugh, fractions, but we're going to do minimal fractions. And then if I'm going between my point and this asymptote, I'm going to test +1. And then I'm going to test 2 points further on to the right of this very rightmost vertical asymptote. It lies at 2, so I'm going to test 3 and 4. With all of that information, I'm going to have a decent idea of what this graph is going to look like. So the way we test them is we plug these values into the original equation. So -3 squared all over squared plus 3 minus 2, like this, which gives you 9/10. So almost 1 is where I'm at whenever I'm at -3. So I'm right here at almost 1. It's 1, 2, 3 right here. But when I do 2, -2, I get 4 over 4. Oh, this is 1 that does that. That puts me at 1. And you're like, yeah, that's on our asymptote. Yeah, we can cross our horizontal asymptotes. I forgot this one did that one. So, I don't know about you, but if this was the only 2 numbers I got, and I knew I could cross this one, but I can't cross that one, then I know that it's going to go like this. And then I may want to test a couple more numbers, but here's what else I know. I don't want this to just shoot off down here and head off to nowhere land. Because what does my graph have to do around its asymptotes? It's got to hug it. So even though I crossed this horizontal asymptote, it's going to come back up and hug it at some point. This is the one that I put in here on purpose so that you can see that you can cross it. Again, I will never give you one that crosses on a test because I don't like them. They frustrate me. And I don't think they make as pretty graphs. But that's neither here nor there. All right, so for the next one, -1/2. That'd be 1/4 over 1/4 plus 1/2 minus 2. Do lots of algebra there, and you get -1/5. So that's like barely down here. And then 1 would be 1 over 1 minus 1 minus 2, which is -1/2. So this one, we know we got a hug here on the left, and we're going to have to hug over here on the right. So it kind of looks like an upside down parabola there in the middle section. All right, 3, we would have 9 over 9 minus 3 minus 2, which is 9/4, which is about 2 1/4. So we're up at 1, 2, and a little bit. Then for 4, we're at 16 over 16 minus 4 minus 2, which is 16 over 10, which is a 1.6. So like 1.5-ish. So we get these 2 points, and if, huh? Yeah, I mean, there's not much there. But even with those 2 points, I can tell that I'm going to hug over here, and I'm going to hug over here. I believe, which I haven't made your assignment yet, but because I haven't made it yet, I'm probably going to make all of these to where they're matching. I mean, you'll have to find all the bits and pieces, but hopefully, I don't think they come with a bunch where you actually have to do the actual graphing. So you'd have to be able to find the one that looks the most like this. So this is one of the weird ones where you would or could cross that horizontal asymptote. And because I didn't flip over onto the back page, I had skipped one, and I'm sorry about that. So let's go back and get that one real quick. Where is that one? I have too many pages of notes. It's not that one. It's this one. Are we ready to go back to the flip over? Okay. Let's go back. This is the one we should have started with. This one plays by all the nice rules. This one's 2x plus 3 over 3x squared plus 7x minus 6. So, step 1. Find our y-intercept by plugging in 0. We get 0 plus 3 over 0 plus 0 minus 6, which is -1/2. So 0, -1/2 will be our y-intercept. 2, we find our x-intercept, and that's by taking the numerator or the top and setting it equal to 0. 2x plus 3 equals 0. Subtract the 3. Divide by 2. And I find that I have -3/2, comma 0 as my x-intercept. Step 3 is my vertical asymptotes. We find that by setting our denominator equal to 0. Our denominator is a quadratic. So let's try and factor that bad boy. We'll have a 3x and an x. Then we're going to have to test some stuff out. Factors of 6 multiplied by 3, that'll give us 7. Yeah, we're probably going to use 2 and 3. Maybe a -2 and a +3. Because if we do first, we get 3x squared. Then we'll get a positive 9 minus 2, which will give us a positive 7 and a negative 6. Then we set each of those equal to 0 to find where our asymptotes are going to lie. So we have vertical asymptotes at x equals -3 and at x equals positive 2/3. Step 4, let's look at the degree of the top versus the degree of the bottom for our horizontal asymptotes. The degree of the top is what? 1. Degree of the bottom is 2. So we have n is less than m, and when n is less than m, what do we know? Yeah, we have horizontal asymptote at y equals 0. So we got a lot of information. So let's graph all this information. We've got a horizontal asymptote at y equals 0. Can't really see it all that well. So just make a little note of it there so you don't cross that. Or you can, but I'm not going to let, this one's not going to play mean. X equals -3, 1, 2, 3. We have a vertical asymptote. And x equals 2/3. So that one's almost at 1. I had 0, -1/2 as my y-intercept. And I had -3/2. 0 is my x-intercept. So I can pretty well determine at least partially what's going to happen in here, a little bit, based on those two intercepts and the fact that I have this asymptote right over here. I bet you I'm going to connect those, and it's going to hug going down to this right-hand side. But since I don't know that for sure, that's why we do those test points. Okay? We do a test point between our point and our asymptote, between this point and this asymptote, and then do 2 on either side. I know we're out of class time, so I will let you know that in my notes I have a table to where it shows you this stuff. But the next one would be right here, and then there's, so it would look almost like one of our cubics here in the middle. And you would know this by testing your points. And then over here, it's going to hug like this, and it would hug like this. I didn't just make that stuff up. I did make a table. You can see those functions and values in the table. Okay, so this is the final example where we are graphing x to the third plus x squared minus 20x all over the x squared minus 5x minus 14. Remember from earlier on that there are like certain steps or rules that you want to go through whenever you are solving these rational functions. And step 1 is going to be finding what? Finding your y-intercept. That's right. So step 1 is where we're going to find f of 0, which means anywhere in this function that there's an x, we're going to have a 0. So on top we have 0, 0, 0. So that's nice. On bottom we have 0, 0, minus 14. 0 divided by negative 14 is 0. Step 1 should always be pretty easy. Step 2 is what? Find our x-intercepts, our solutions, our zeros, however you want to think about it. And the way that we do that is we set our numerator, our top, equal to 0. So we have x to the third plus x squared minus 20x equals 0. And we need to solve this. Looking at it, I know that every term on the left-hand side has an x, so I'm going to factor that out to get started with. Because when I do that, it's going to leave me with a nice quadratic here inside this set of parentheses, so that I can factor it into two binomials. The sign in front of my c is negative, so I know I'm going to have a positive negative. I need factors of 20 that subtract together to give me a positive x. 5 and 4. And since it's a positive x, I need more positives than negatives. So I'm going to factor it just like this. To find those zeros, I would set each of those factors equal to 0. Now, most students do fine with this, but don't forget about this x that's already factored out front. That means x equals 0. X plus 5 means we have x equals negative 5, and x minus 4 equals x equals positive 4. We have 3 different zeros going on here. So 9 times out of 10, if a student misgraphs or missolves this, it's because they forget about this x equals 0 bit out here, and that'll mess up your examples at the end. So this is the point 0, 0, negative 5, 0, and 4, 0. I just like to have all that written there so that when I go to plot my points, they're all nice and ready for me. Okay, what's step 3? Vertical asymptotes. And we find our vertical asymptotes by setting our denominator equal to 0. So we set our top equal to 0 for step 2. Now we're going to set our bottom equal to 0 for step 3. X squared minus 5x minus 14 equals 0. The nice thing is 14 doesn't have very many factors. 1 and 14 and 2 and 7. And we need factors that are going to subtract together to give me 5. Negative 5, so I'm going to have negative 7 and a positive 2. So I'm going to have vertical asymptotes at x equals 7 and at x equals negative 2. This is also where I would find the domain of my function if I so needed it. Because my domain, remember, of a function is negative infinity to positive infinity, but we would take out the points where each of those asymptotes happen. So we'd take out the negative 2 and we'd take out the positive 7. Now, we don't have to do that on this problem, but I wanted to state it so that you know if it does ask you for your domain, this is the step where you would get it. All right, step 4 is horizontal asymptotes. Horizontal asymptotes is where we look at the power of our numerator over the power of our denominator. And there was 3 different cases that could happen. So what is the power of our numerator at the top? What is the highest exponent on top? 3. And what is the highest exponent or power on bottom? 2. So we have then that n is greater than m. And when that happens, what does that tell us? There's no horizontal asymptotes, okay? But how do we know if there's oblique asymptotes? What's the special rule for oblique asymptotes?
The numerator is higher than the denominator by 1.
That's right. If our n is greater than our m by just one number, by one power, then we have oblique asymptotes. So that happens here. Our top is bigger than our bottom by just one number, so we are going to have oblique asymptotes. Now we got to figure out where. Because oblique asymptotes, we are going to get a linear equation for our asymptote instead of just like x equals or y equals. So here's how you figure out what these asymptotes are. You're going to take your top, you're doing long division. You're going to take your numerator, the x to the third plus x squared minus 20x, and you're going to divide it by your denominator, the x squared minus 5x minus 14. whatever we get on top of our division bar is going to be the equation for our oblique asymptote. So we have x squared, and we wanted to get to x to the third. What do we multiply it by? X. X times x squared will give us x to the third. X times negative 5x will give us a negative 5x squared. X times negative 14 will give us a negative 14x. Then we draw the line, change the signs, so that our x to the thirds go away. We have 6x squared minus 6x, and there's nothing left to bring down. So what do I multiply x squared by to get me to 6x squared? 6. 6 times x squared will give me 6x squared. 6 times negative 5x will give me a negative 30x. 6 times negative 14 will give me a negative 84. Draw my line, change my signs, and I get 24x plus 84. Now, there's no way I can get x squared to give me 24x because the powers are down, and so this would have all been our remainder down here, but we don't need to worry about our remainder. All we worry about is this x plus 6. That is the equation for our oblique asymptote. Y equals x plus 6. So we found our x-intercept, we found our y-intercept, our x-intercepts, we found our vertical asymptotes, we found our horizontal asymptotes, which we don't have any, we found our oblique asymptote, all kinds of asymptotes. Now, we graph everything that we have, and then we have to do our table to find all these other things. So, what we do know is we have a y-intercept at 0, 0, which is also our x-intercept there. We have an x-intercept at negative 5, 0. 1, 2, 3, 4, 5. We have an x-intercept at 4, 0. 1, 2, 3, 4. We have vertical asymptotes at x equals 7. 5, 6, 7. And at x equals negative 2. And we have that oblique asymptote causing all kinds of a mess at y equals x plus 6. So we graph this just like a line, because it is a line. Y equals x plus 6. When x is 0, y is what? 6. 1, 2, 3, 4, 5, 6. So I'm going to put a little dot there. And then my slope of that line is positive 1. So I'd go up 1 to the right 1 to graph my slope. I use my y-intercept, graph my slope, going to connect it, and I'm going to use a dashed line because this is an asymptote. I'm going to try and get it to not be too wonky. All kinds of fun in here. This is why I don't like the oblique asymptotes. Kind of just run through the middle and cause all kinds of problems. Okay, so we've done all of this fun, and we have no graph. So we need to pick points as best as we can that fall in between all of our asymptotes and all of the points that we have. So I need to pick a point between here and this asymptote. So I'm going to go down here and pick negative 7 and negative 6. And I pick negative 4 and negative 3. And I pick negative 1 and positive 1 and positive 2 and positive 5. And I pick positive 6 and 8 and 9. I'm not even joking. It's a lot of stuff. Pick all these points because there's all those different gaps that we have to figure out what's going on between the x-intercept, or the zero that we found, and all of these different asymptotes. Because we've got two vertical asymptotes, we've got that horizontal, or that oblique asymptote, which causes problems, and then we've got to figure out what's going on at the ends as well. Because if you notice that on this graph, when we drew in our asymptotes, notice we don't have any x-intercepts over here or way over here. That doesn't mean that nothing's happening over there. We need to figure out what's happening over there. Again, this is why I am never going to give you one of these on a test, because this is gross, right? Okay, so trust me for a minute that you have access to these values, okay? You can go copy them all down on your own if you really want to. Here's what's going to happen with our graph. And way up here in no man's land is another swoop, because this happens at 8:41.6 and 9:28.64. And I did not make 41.6 or 28.64 little dash marks. So it's just happening way up there, way above that oblique asymptote. And yeah. So this is a nice, fun one. And this is one to show you all of the mean things that can happen in a graph. Because as you can see, we cross our oblique asymptote, because why not? We still hug it, but we're going to cross it. And then we've got, this guy way up here doing whatever he wants to do, because that's what he wants to do. Where it's going to hug on this side, it's going to hug this asymptote, and then this bottom part's going to hug that oblique asymptote once it's up there. So all of this to say, they can be really fun, quote unquote, and I'm not that mean.